Alright, so welcome to my channel. In this video I would like to show how to use FreeBSD for FPGA development. In this video I'm going to give also a short introduction to what is an FPGA and Verilog, the hardware description language. I'm going to give a small overview about a project that I've been working on. I'm going to show how to simulate this project. And since this is one of my favorite topics, I'm going to show how to do a buffer overflow on the RISC-V 32-bit CPU. For that, I'm going to be using GCC to compile the project for the RISC-V CPU. The CPU itself is going to be described in Verilog, so I'm going to be using Icarus Verilog. And for the waveform viewer, I'm going to use GTKWave. An FPGA is the short name for a field programmable gate array. Here on the right hand side we can see an example from Lattice. When you have a chip, you have some logic around. This will be connecting to the individual pins of the FPGA. And then you have the green part where you have some programmable logic blocks and some interconnects. These logic blocks can be programmed using lookup tables or, for example, small memory elements like D flip-flops, and can be connected to each other through the programmable interconnect lines. By this way, we can define any logic circuit that we would like to have at the hardware level. On the left-hand side, you can see an icebreaker, which is a really nice board for beginners for FPGA. The nice thing about this board is that you can use open source synthesis tools. So here is a very short introduction to Verilog HDL. HDL standing for Hardware Description Language. This is not going to be an extensive tutorial. In any case, there are awesome videos available on YouTube. I advise you, if you are interested, to have a look at them. Verilog is a programming language that describes hardware. So what we're doing in the language is we are writing a program that is going to result in hardware. Can be synthesized to hardware. On the right-hand side, you see an example of the hardware resulting from the code on the left-hand side. The details on how the mux is implemented with gates is currently not shown, but it's just shown as an example that we have an output which is 16 bits wide. We have 4 inputs, A, B, C, and D, which are 16 bits wide, and a select line which is 2 bits wide. Here we see the same description in the module, in the interface. So the MUX4 has an input, the select line 2 bits, 1 and 0, A from 15 down to 0, B, and so on. And the output is going to be also 16 bits from 15 down to 0. The output is going to be put in a register because we are going to assign values to it. And the logic of this block says that at any event, this means the always star, do a case on the cell line. Whenever it's 0, 0, then the output becomes A. If it is 0, 1, the output becomes B, and etc. So this is a very simple example on how to use Verilog HDL. Using this kind of hardware description languages, we can build entire circuits which are very complex, and we can even build ASICs, where an ASIC stands for Application-Specific Integrated Circuit. This is also an awesome way to prototype new ideas before they go into production. On this next slide, I'm showing you how the project that I'm working on currently looks like. Here on the left hand side, on the top, we see source files. These are source files that contain code that is going to be compiled specifically for the RISC-V CPU. Therefore, we need the compiler. This is GCC. And I wrote a small program that translates an ELF object into an hexadecimal file because we need to add this as the input for the memory elements. The generated hexadecimal files gets fed into a Verilog code, which contains the CPU, contains the system on chip, contains several elements, and this all this code can be fed into a Verilog compiler that we see here on the right hand side, or it can be synthesized. The lower part I'm not going to show in this video. This would mean that we'll be doing an FPGA programming, so we can really get hardware running our examples, for example with the icebreaker. In this part I'm going to look at the upper part of this diagram, and here I see some additional source files that are compiled with GCC. This means that I'm going to have some virtual elements, some virtual peripherals that I decided to create, and I'm going to have two of them, an LCD, liquid crystal display, and I'm going to have an UART that is going to connect to the console. This Verilog compiler is going to generate some files that I can run into my simulator, VVP. And after the simulation is run, when the simulation is being run, I can interact with my peripherals. So the code that is added to the source file can do this interaction, or I can interact directly with the keyboard. This is this small sign here for the keyboard. After a certain amount of time, simulation stops and I can have a look at the waveforms that are generated. Let's have a look at a more detailed view of the Verilog code, and in particular on the architecture. Here we see a RISC-V CPU running with 32 bits only, so it's the variant RV32i that I took from the website, from the FPGA Learn, from Bruno Levi. It's a BSD3 clause license, which is pretty nice. And I decided to include this in my project. Here we see we have a clock that is going to be the 12 megahertz running in the icebreaker, although I'm currently not synthesizing the project. We have the reset line, which is going to reset the CPU. And the CPU is going to run programs from memory, so we need to have the connection to the memory here. This memory is going to be initialized with the hex values that we've just seen before after being compiled by GCC. And in order to access other peripherals, I need to have a small logic that I call here the decoder, that is just going to output the lines on the read-write when the memories are, when the CPU wants to read from memory, or wants to read or write to the UART interface or to the LCD. The LCD currently has no output that the CPU can read, but the memory and the UART peripherals, the peripheral is connected back through a multiplexer, which is also addressed here by the decoder. All right, so let's have a look at the source code. So here I'm at the project and I look into my files. The first file that I see here is the RISC-V CPU. This is the system on chip, meaning that this is integrating the UART and the LCD and the memory. That is basically the picture we've seen before. And we have the test bench that is just going to generate the stimuli to run the demonstrator. We see here some virtual modules, so an LCD module here and an UART dash.c. Let's have a short look at UART.c. Here we can see that it's using a Verilog VPI. I'm not going to go into too much details here, but basically it connects to the terminal. It reads the keys from the keyboard, from the terminal, and it outputs them back into the test bench. The LCD module is also similar. It uses shared memory to connect to an external GUI element. This module is going to simulate an LCD module AC1624. All right, let's see some other files here. This is coming from the Bruno Levy's website, and I've just used it without too many changes. There is one change that I've done though, which is the bench. Here I decided to put some wires that I can look at the internal registers of the CPU. And if I search for bench here, this is going to be important later on. This is just for the simulation purposes. If the program counter is currently higher than 800 hexadecimal, I'm going to stop the execution. This is going to be a kind of a breakpoint when I do the demo for the buffer overflow. For now, we can just ignore this. This should never happen. So this is the high-level view of the components. We basically have the input for the clock and the reset, which we have seen before. We have here, let's put like this. So we have here a couple of descriptions for some wires and some connections. This is going to be the decoder logic that we have seen before. And here is reading of the hexadecimal file that I call the firmware.hex. We'll have a look at this. And this is whenever we want to read the memory, we basically set, so actually this is writing to the memory. We get the data from the RAM depending on the mask, or we write it like in this line here. All right. This is a component that cannot be synthesized, but corresponds to a UART that is going to give me the connection to the serial port that's connected to the terminal. Down here we have the CPU with all the ports connected, the clock signal, the memory address, write data, the write mask, the read data, read strobe, read busy, write busy, and the reset pin. And we have the LCD interface for the AC1624. Here's the test bench. It just has the two signals, the clock and the reset. And it just asserts the reset for three clock signals, and has another small task here, so meaning that the clock starts at 0 and every simulation tick it negates, so it flips from 0 to 1, 0 to 1, 0 to 1, 1 to 0. Here we have another small tasks that we write to the screen starting the simulation. After 500,000 simulation ticks, we write the carriage return and we finish the simulation. And here is the one that this task here basically shows us that we're going to dump all the variables into the dump VCD and the variables corresponding to this test bench. So all the signals. All right. Now let's have a look at LCD. The LCD is an external peripheral. So basically we have the lcd.cpp. This is a very small program that just creates a widget to draw some lines and creates a display. We can compile this and we can make it run. Let's do it like this. All right, we see here, and we started the simulation of a small panel that I'm going to say here layer on top. And I'm just going to let this run in the background because it's going to give us the LCD. Currently it's all blue because it's turned off. Okay, now let's have a look at the source file. So here we have, let's start by the test.c. Test.c is the program that I'm going to compile as for the 32-bit CPU. I created a couple of functions here, so we don't have access, since this is embedded development, we don't have access to the libc, at least not yet. So I've created my own functions to get the string length, to put a string in the UART, the UART put char, to do a memset, UART read, UART get string. This is a very bad function because it gets a string until a carriage returns. So this is where very simply a buffer overflow can happen. A small delay if we need, put a string on the LCD, initialize the LCD, reset, and change the address on the line for the LCD. Okay, now let's go to the main function. The main function just starts by calling the UART put string on the string that I've defined before. So this just prints out this copyright thing here. We should see this at the console because this is at the UART. Here we initialize the LCD and we put the string, enter string. Then we call our main program. Our main program is going to be just a processing input function. So it's just going to be an infinite loop where we have a buffer of 10 characters. We put into our serial console string. We get the string on the buffer. So here a buffer overflow is pre-programmed. Then we just put the string back into the console. As easy as that. So here is the example for the memset, the small delay, how to do the LCD init, etc. So how to put the string. And what we're going to see is that we have a function here that I name it not called, that just says UART put string well done. This function is not called from anywhere. So let's search not called. If I search, basically it's not being called anywhere. Let's go to the beginning of the file, search for it. It's just at this line. Okay. There is another function, another small program that I created called the convert.c. This is takes an Intel hex file and converts it into hexadecimal values that are required for the Verilog memory to initialize the memory. Let's see. Then we have the LDS. This is for the linker script. Basically, this script says that we need to put a CRT, the C runtime, and we put at the start address 0, then we have the text segment and the data segment. And what I didn't show yet was the C runtime. We need to do a small initialization here. This initialization is going to be like this. So currently I'm simulating 64 kilobytes of memory. And I put here, this is the reset address, and I put I load the stack pointer to the lowest memory address, and I jump to the function called main. And here the CRT stop basically it's an infinite loop in case that we return from main. We don't start executing some crazy stuff. So this is how the program starts. It starts at memory location 0. Let's try to compile this. Make. So you see here, I'm using the RISC-32 unknown ELF GCC. This is available in the FreeBSD package repository. Let's have a look at the main file. So in order to generate the test.hex, we need a ihex, and we need the convert script. The ihex is done by copying the object from the test to the Intel hex format. This is needs the test needs the test.o, test.s. It does the compilation here with the crt.o, etc. The convert just gives me the convert utility that I created and I explained before, and the clean just cleans the project. So I just compiled everything. So here is was my convert. So here is my convert file. Here is the program tests. We can say file test. This is a RISC-V executable, a 32-bit. And we have our hex file. Let's have a look at the head. Let's take 20 on this file. And this is the program that resulted out of the compilation process. Let's have a look at the object bump. -d. Test, this is the file we just compiled, and let's pipe it through less. And we see here this is coming from the CRT. We have the reset, so we had this 37, etc. This is the instructions I've shown before that initializes the stack pointer, and just with the infinite loop for the stop. Then we have the function process input. That was defined in the C file. We have the main program, we have the main function, we have the memset, we have a couple of them here. And let's see, we should also have the not called function. Let's go down, get string, not called. Okay, the not called function is at offset 698 hexadecimal. This will come in handy later on. For now, we have our hexadecimal file, and this test.hex is going to be used later on for our, it's going to be the firmware for our Verilog code. So let's go one step back. And let's have a look at, first let me try type in make. Oops, okay. So it actually did already everything. And here it's asking enter a string, and the simulation has stopped. So we see here, basically I've done this all automatic. You see here enter string. This was what was supposed to happen with the file. So let's see the source, test.c. Let's go up to the main. Let's search the main. The main function, it says in the LCD put string. Let's put here BSD rules. Okay. And make clean. And let's try again to make. And we see here BSD rules. Okay. Then BSD Jedi. Okay. And what we have seen, I'm going to have a look at this, the waveform in soon. You've seen that there is an output here, starting simulation, then the copyright, those lines that we saw, then we have the string BSD Jedi, that was the input, and then it was echoed back. Then it asked again, because this is the infinite loop for the main program, and the simulation was stopped after 500,001 simulation ticks. Then automatically we were calling GTKWave that we can now use to analyze. So I'm going to stop the LCD simulator for the time being. We're not going to need this anymore, served its purpose. Here we see the test bench and the device under test. We have the LCD and we have the CPU. And for this device, there are a couple of lines that we could have a look at. I'm in particular interested in looking at the clock line. So here we see the clock line going up and down, and the reset line. If you remember, we saw that the reset was 3 clock cycles. So It starts here, goes up. Okay, let's zoom out a little bit. Okay, it's apparent. No, the reset is active low. Okay, so that was good that I saw this. Let's zoom in again. So let's see if the 3. So 1, 2, 3. So it was not 3 clock cycles, but 3 simulation ticks. Which one tick means clock low, another tick clock high, another tick clock low. And you see here reset has been asserted from the beginning. It's at 0. I can put a cursor here so you can see it's a reset is at 0. And after this time reset becomes 1. And it always becomes 1. I can zoom out, zoom out, zoom out, zoom out. And you see the microseconds here. It simulated about 500 microseconds. After this, we just see the reset signal is always up. All right, let's have a look at the, for example, the memory address for the I/O, the LCD write strobe. Actually, this one. And we see that here, so let's zoom in a little bit to this area. So initially the CPU does a couple of things. We see the reset had happened here. So if we zoom again back in, we see it very small here, the reset. So let's zoom out again. And at some point we had this part here. This is a write strobe to the LCD. So if you remember, there was a message that was put in the LCD. So then let's see what is written to the LCD. Memory write data, we can put it here. There are some red things, is okay. Next, and let's do a zoom in. So here we can see okay, so this is the first time that we have anything written, and it's a 3/8 hexadecimal. Let's see where does this come from. I need to open a new terminal. cd source vimtest.c, and let's have a look at this routine LCD init. The first thing that we write is a 3/8 hexadecimal, then a 0E 0106. All right, let's see. So 3/8 is a little bit small, but it's a 3/8. 0E 0106. All right, 3/8 0E 0106. And after that, we had written the put string. We call the put string here. So this means that the next value was here a 2 with 42. Okay, let's try to see if we can interpret this by changing the data format to an ASCII format, and we see there is something there with a B. Okay, B, no, this is not what I want, so I want here, and jump to the next one. B, S, D, this is a space bar, or R, U, L, E, S, question, exclamation mark. BSD rules. Yes, this is what we have seen in the LCD. And this was the last pulse that we have seen that came out to the LCD. And this is basically how it's working here. All right, now let's see the UART. Can we get the UART here? So let's search for a strobe. That would be the read strobe. Actually, let's go for the write strobe. Or no, don't want to do that. Let's have a look at which line would you like to have. So we have the IO read, IO write, So we want to see what came from the keyboard. That would be the I/O write, but not the strobe. We want the data, the R data, the UART read data. So let's see the UART, the read data, this signal. Let's put it here and let's zoom out. All right, we see something here already. So let's try to advance there. Here, let's try to see what happened. And we see here something. Okay, again, since we were doing stuff in hexadecimal, let's put this data format, not hexadecimal. This is being shown in hexadecimal. We want to see it in ASCII. So it's BSD rules. Okay, so this was the message that I also typed in at the keyboard, BSD rules. Very nice. And you can see that the keystrokes, they happened in not a regular time interval. Can we see the data that that when it was printed out? That should be the I/O write data. So let's try the I/O write data. So after this happened, the keyboard, after I pressed enter, there should be here some okay, then we need the write strobe. When do we want to write there? Okay. And there are some write strobes here with some data. Okay. Okay, so this was the echo back. You can see when I was typing the keys, there was some echo apparently. And here at this position, let me see, let's zoom in. We have here this part, so 0A, I can see already it's a carriage return, but let's convert this to ASCII. Okay, this is a carriage return. Let's go for the next write strobe, BSD rules, or with J. Okay, did I put with J? Ah, BSD Jedi. Ah, the font is a little bit too small. Okay, BSD Jedi, not BSD rules. I'm sorry, but I cannot make this larger. So if you want to see it, I also have problems here in my computer because I don't know exactly how to make the waveforms, these values here, larger in GTKWave. So other than changing the screen resolution, but you get the point. So how this is how this is working. So we see some activity here in the beginning in the I/O strobe, meaning that this was the initial message that was put out. So the message went to the console in the beginning. Then we see some activity on the LCD. Then here's some activity also in the console, and then nothing happened. Then there was some irregular conversation here with the UART. This is what was the when I was typing in things, and then at the end there was a big burst here, which was basically the printing out again the things. So why did we see those stuff there? We saw it because when I was typing in the letters, they were being echoed back, and when I pressed return, the entire string was echoed back. Let's see this in the code, that this is the case. So source test.c. Here is the initial part where we have the put string. Then we have the process input, and then again we put string after the LCD has been initialized, and we put the message in the LCD, and then we have the get string, and here is where the echo is happening. So let's see. I'm not going to go into the details explaining this, but here we see UART put char. So this is what is currently doing the echo back. If I remove this put char, nothing is going to be printed out. Let's just do it for the time being. So I copy these lines, and here, and you can see that it goes to C. If it is a carriage return, then it breaks. Breaks means that the get string is finalized. So let's do again a run of the simulation. So make clean and all. Should be doing the same thing. Okay, make and hello FreeBSD. We see nothing, but now pressing enter, we see the feedback of the entire string comes out. Okay. And we can pull the things. I think I have recorded already. So read. So there is a test here. Yes, so most of the signals that I'm interested in are already here. And it puts out all the points. So the we see here the irregular characters that come in. Let's have a look at this. Yes. So again, convert this to ASCII, H, E, he, low, space, FreeBSD. And then there was the carriage return. All right. And then the burst happened. The output burst happened here, as you can see. All right, I think we can understand relatively well what's happening here. Now let's try to see if I can cause a buffer overflow. So what I'm going to and try to call the not called function. So this is now going to be a little bit fun. So the first thing that I need to know is, because this is an interaction with the keyboard, and typically how you're going to do these things in practice, you're going to do some printf, something here, and then the program, something like this, meaning that you're going to try to print something here and enter it to the standard input for the program. This is currently not really possible, at least in this way with the simulator, with the simulated program, because there is no handshake, no anything. So the output that is going to come from here is too fast for my simulation test bench. So there is a really nice program that's called PV. So PV can be worked more or less like this. So echo hello world, and I can cat into PV QL, let's say 5, and let's see what happens. Okay, as you can see, it's printing hello world pretty slow. Let's put it even less, 1 character per second. H, E. Okay, so this is going to allow me to simulate keystrokes really slowly, slow keystrokes, and is going to eliminate the handshake problem. The next thing is I cannot start outputting things immediately when the simulation starts, because there is the initial logo that is printed out and the LCD is initialized, etc. So I need to know how much time does it take the simulation until it goes to the string. The first thing I'm going to do actually is going to go to the source. Let's go to this directory and undo what I've done before. So because I want this feedback to be there. Okay. Now, Now, one way to see how much time does it take, I'm going to make it in a way that is reproducible. And the way that I'm going to make it reproducible is going to be typing it make, and then there is another target. So let's have a look at, okay, edit the file. So I want to have the, I don't want to start GTKWave by default, so I want to have only the dump VCD. So this is what I'm going to have here. You can see here are the commands that I use for the UART. So I compile the UART, I compile the firmware, so I go to the source directory and I make the test. Actually, let me say here, just to be sure, clean and test, just to make sure that everything is fine. Then I copy the test hex into the firmware text hex, and that's it. Nothing too fancy. Okay. This means I want to time make clean, just to make sure everything starts clean from the beginning. And the make clean takes about 1 second. Let's try it again. About 1 second, about 1 second. So I need to take into consideration that keys cannot be started before 1 second. I cannot start with the keystrokes. And the other thing, let's go up here a little bit. And the other thing is I want to wait for the string here. So first I want to have all this output and so on, and then when it's asking for string, then I can start with my keyboard. How do I stop the simulator there? Then I also need to count the time, and for that I came up with an idea, which is running an expect script. So you can install the expect, you just spawn the make dump VCD and expect string, and then just stops the program. So whenever there is a string being asked for, then it stops. So I'm going to make clean, just to make sure everything is fine. Then time on the test exp. All right, let's try it. Compiles everything, right? Okay, 1.5 seconds that it took only to run the simulation. It doesn't account for the time for cleaning. Go and again, 1.5, 1.4. Okay, it's about 1.6 plus the other one. Let's say in total we can wait 3 seconds. Let me see if I can count this. So time, I'm not sure if I can do, no, I cannot do it like this. Let's try to repeat the experiment. All right, so let's first try to see if our concept works. So I sleep for 3 seconds, then I echo hello world. I need to put a carriage return at the end, and this means that here actually I need a printf. And after this, then I need to pipe this into PV quiet, and let's say I'm going to be a little bit bold and put 20 characters per second. I think according to my experiments this actually worked. And before quitting, let's just the CPU run a little bit further. Just let's sleep for 2 seconds. Okay, so this is now our input, and we're going to pipe it into make clean and dump.vcd. Okay, this looks more complicated than what it is. Let's run. Compiles, runs, string, oh, hello world, string, hello world. Okay, now it's asking string, etc. Yeah. Okay, so it doesn't really matter what happened in the end, but what really was important here was that we had the hello world that was input, and then we had hello world that was echoed back. So we can do some things here. Now, what I'm going to try is to try the following. if you remember, so let's just run with x66, and instead of sleeping 2, let's maybe just sleep 1. I think that was too much. Okay, string x66, string x66. It's probably still a little bit too much, but it doesn't matter. As long as it's running, I'm happy. And everything is going fine. But now, if you remember, what was this? femto-rv, took the quark model. If you remember, I said that if the program counter is higher than 800 hexadecimal, then Houston, we have a problem. We're going to output a stop at this address, finish the simulation immediately, and saying, okay, the program counter now was at a value that I didn't like. So now let's try to go exactly for that case. And how can we go for this case? We can go for this case by trying to put lots of x's and cause a buffer overflow. I don't know how many I put, but let's just go with this. And if we are lucky, I don't need to know exactly how the assembly code is working and so on, but let's just try and see what happens. Okay. String, we put lots of x's, and boom, stopped at 787878. Okay, so this means that I'm now controlling the program counter. This is pretty bad for sure, that I'm able to control the program counter. This means that I can, after this, I can basically do whatever I want with the program counter. Now, I see 7878, so let's try to see what is this 78. I go here to the other terminal, I increase the font a little bit, Vim, and I know that I've put lots of x's, and let's see what is the ASCII code for for x. And we can see here that x is number 120 or hexadecimal 78, octal 170, doesn't matter. Hexadecimal 78. So this means that we have here 787878, means x. Somewhere here in the x's, we were able to overwrite the instruction pointer. Now the question would be where, at which location did we do it? There is one way to find it out. So I need a non-repeatable pattern. Let's say like this. I think it should be enough. Let's try it out. Okay, good. And now it has stopped at 71707C. Find out where it was by looking at an ASCII table. Here I have an ASCII table from Wikipedia. From Wikimedia. And we have 71 here. So let's have a look at 71 hexadecimal. 71 is a Q. So let's write here Q. Then we have 70 P. And then we have 6C. 6CL. Okay, so Q could be here, or it could be here. And we see already that there is an L nearby, so L, P, and Q, or Q, P, and L, but they are written the other way around. So now let's try the following. There is a really nice trick that you can remember for these things, which is that the hexadecimal 30 corresponds to the character 0, 3 is 39. So this was when the ASCII table was designed, this was done on purpose. So if I write the number 0, 1, 2, and so on, I will see definitely a 30 hexadecimal, 31, and so on. And I can immediately know what is the code that I wrote. So first I copied the part until KO there, And now I'm going to write 444, or actually 444, I don't know, 456. Let's try 456, run the thing. Okay, 456, and what do I see here? 34, 35, 36. All right, this is now means that at exactly this offset here, I can control the instruction pointer and I can write whatever I want there in theory. There is another really nice way to find out this offset. We've done it by hand. I can also use a small program that I just wrote here. I want to have a pattern for 30 characters, so I can have stuff like this. And if I ask for the pattern at offset here, then it's going to give me at offset 17. If I ask at offset here, then it's at offset 3. 0, 1, 2, and 3. So it starts at offset 3 here. All right. Just by it, let's try with the 0. Of course, it starts there at offset 0. And maybe too many examples, but let's just try this one here. It's at offset 1, as to be expected. Although I wrote this tool myself, there is an equivalent tool in the Kali Linux. So if you want to check out Kali Linux, you can also check it out. And there is the pattern is also available there. I just decided to write my own version. This version supports actually a couple more flags, a couple more stuff. So it has two different kinds of patterns, but let's not go over this now. Good, so I can have the pattern with 30, this should be enough. Now let's try to put the pattern here. So what we can see is, let me put another parenthesis here. So I want to run two things inside this. Actually, let me stop Vim pattern, I think, or pattern 6. Pattern 6. Okay, it doesn't add the carriage return, but I added here one with N, I think. No, not with N, with R. Okay, so the R adds a carriage return at the end. So let's try again to call the, because we need the carriage return here, so I'm going to call the pattern carriage return and 30 characters. All right, let's try this. So we write the pattern, we get the dump, we get the stop address, and now I can just paste this, so the pattern is also ready to take hexadecimal values. And it says it's an invalid character. Here we have an invalid character. Where is it? The 40. The 40 is here, hexadecimal 40 at, but it's very close to A. It's just at the last bit is set here, and with the 8 the last bit is reset. Actually, if you look at Verilog code, you will see that the memory address basically resets this last bit here to 0, so it's not being used, meaning that the pattern could have been this one here, which it was actually, because it was at offset 24. If we look at the previous experiment that we have done, let's just count the offset. So here was at, where was it? So here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we got here the number 24 by a systematic method. Do you remember what was the memory address of the not called function? Let's try it out. So nm test, so actually source and test, and let's pipe it over grep not called, and we can see here that the address was 0698. Now let's try to inject that, but before we do this, I like to go always step by step, and therefore I'm going to do two things. So here, first a pattern of 24, so I'm just a little bit lazy here. I don't want to write the 24 letters, and after this then a print f of what, and here actually I don't want the carriage return, and 456 with a carriage return. Now let's see if we can get if this is working. Zack, 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 zack. Okay, looks good. Yeah, 343536. So it's working. We are writing exactly the payload at the address that we want. And now I'm going to write hexadecimal AABBCC just for the fun. Okay, let's try. In hexadecimal, some crazy characters are going to appear here, and we're going to stop at AA6262, which was not supposed to happen. Yeah, okay. Because of course we need hexadecimal here. You see, this is why I really like to test things out slowly. Let's try again. You forget just a little bit something, and nothing works afterwards. Okay, we have AA, BB, and CC. Now let's just put the memory address that we had before, which was the 98, so it has to be written the other way around. 98 and 06. Here we can have the 00 because we are only stopping at the carriage return. And now we should see some different message in the screen, because this is the not called function is going to be called. Let's see. And zack, zack, zack. Well done. Very nice. This message, the well done message, comes from the source file. This one here. Let's see. Let's go back here. On the source test.c, the not called is here. Well done. We can also put it here. Well done. Just to make it nicer, you just caused just demoed arc injection. All right, so let's do this. Make. No, not the make like this. So at the source, make, and object nm test grep not called. Is it still? No, it's now at a different address. It's at address BC. So let's 6B and C. BC. Let's try. Check, 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 check. Well done. You just demoed an arc injection. Alright, that's it. If you like this video, please give it a thumbs up. This makes me pretty happy and makes me want to do more videos. Other than this, I wish you all the best. Have a nice day, a great day, and see you next time. Bye bye.